Now that we've conquered confidence intervals for a single proportion, we move on to two proportions. If we take a look at the mechanics, it looks a little bit overwhelming at first, but upon closer look, the statistic just changes from a single proportion to a difference of two. The goal is always to compare two groups, like are men different from women, or is one medicine better than the other medicine, or does one type of boot last longer than another type of boot. So typically this is always going to be a difference of two p-hats. So we replace one p-hat with two. The standard error formula, it looks similar to the standard error formula for one proportion, but variances add that Pythagorean theorem of statistics. So instead of just having the square root of a single p-hat q-hat over n, we have to do the square root of a sum of the p-hats q-hats over n's for the two groups, which is basically one of them squared plus another one squared, take the square root. That formula is in your blue book. And then the confidence interval has exactly the same structure as we had for one proportion. We have, instead of a single p-hat, we have the difference of the two. We still need a z-star. That's found exactly the same way we find it for one proportion. It's a measure of how many standard deviations from the mean we want to go. And then the formula for the standard error. Let's just jump right into a problem. In October 2000, the U.S. Department of Commerce reported the results of a large-scale survey on high school graduation. Researchers contacted more than 25,000 Americans aged 24 years to see if they had finished high school. 84.9% of the males and 88.1% of the females indicated that they had high school diplomas. So we have two different groups now, female and male. And we divided that sample of 25,000 Americans. Of course, it didn't say they were random. Well, we would hope that researchers know what they're doing and that they would have chosen random samples. So the best we can do is assume that they did it the way they should have. So the first question, always, before we can construct a confidence interval, is if the assumptions and conditions for inference are necessary. Assumptions are just things that we assume to be true, but we don't generally write those down, so it's really the conditions we're worried about. The conditions for two proportions are identical to the conditions for one proportion, with the addition of a check to make sure that the two groups are independent. If we have some reason to believe that the males and females have some connection to each other, then we wouldn't be able to do the procedure. But if they pick 25,000 hopefully random Americans, the males and the females ought to be independent groups. It's not like we're picking sisters and brothers. It's not like we're picking husbands and wives. We're just picking a bunch of Americans out of the pot. So I like to combine the two groups are independent with the idea of them being random samples into a single statement, just because I have to write less. So I just want to make sure I clarify both of those things. So I'm going to assume that the 25,000 Americans were a random sample. You could also say a representative sample. That would work. And that the females are independent of the males. So we kill two birds with one stone there. We check our random sample condition and that our two groups are independent of each other. So there's 2 and 1 there. Then we have our 10% condition. Now the catch is you have to check your 10% condition for both groups. So 12,460 males and 12,678 females are each less than 10% of all males and females. So I have to check for both groups, but if I'm smart about how I write it out, I can do it in a single sentence. You can write 2 separate statements about that if you want to work harder. Last condition is the NP and Q condition. Of course, we have P hats and Q hats up here, and there's 2 sets of them. We have successes and failures for males and successes and failures for females. So there's actually 4 different pieces that we have to check. So this one takes the longest, but it has to be done. And I'm going to choose something that's practical for subscripts like M for male and F for female, because any reasonable person is going to understand what that notation means. So the number of males times the proportion p hat of males, or successes, is 12,460 males times 0.881. Oh, wait, wrong number. 0.849. Okay. And that's going to be 10,578. Some nasty big numbers here. 0.54. That's definitely greater than or equal to 10. Okay, N of males times Q hat of males, so the expected failures is 12,460 males multiplied by the rest of that sample. Let's see, if I subtract that from 1, that's 0.151. Okay, and that tallies up to 1,881-ish, 0.46. That's definitely bigger than or equal to 10. Okay, now the females. Successes, number of females times the proportion of females, p hat sub f, that graduated high school, that had diplomas, was 12,678 times 88.1%, so 0.881, and that tallies up to 11,169.32, definitely at least 10. And last but not least, number of females, N sub f, times the failure rate, Q hat of females, is the 12,678 times the other 0.119, 11.9% of them, which is about 1508.68 females, definitely at least 10. So 4 conditions, 2 rolled into the first one, all of them are met. So yes, so we're going to create a 2 proportion Z interval. Now the actual question is on the next slide, so we're kind of jumping ahead to what the next part was. So we have 2 samples that we're comparing, so 2 proportions, and then a Z interval because we are still using the normal curve. Alright, worst part's over. This takes the longest. Okay, so we want to create the actual interval. So to create the actual interval, we want to start with our statistic. Well, we're looking for a difference in graduation rates between males and females. The order in which you do that really doesn't matter. I typically go males minus females if that's the way it's written, but you can do it either way as long as you interpret it correctly. So we need our males first. Males were 84.9%, so 0.849. I want the difference of that in females, so I'm going to subtract the female rate, which is 0.881. And so that combined difference is my new statistic. So this is the difference according to our one sample. It may be wrong, but it's our best guess. Plus or minus a z-score. Well, it's a 95% confidence interval, and we already know, hopefully, that that's a z-score of 1.96, or z-star, times the standard error. And there's a big fat formula for that. The formula says you take your first group, which is my males, and you do p hat, which is 0.849, times q hat, which is 0.151, divide by the sample size, which is 12,460, plus, and then you do the females. So 0.881, successes, p hat for females, times 0.119, the failure for females, over the number of females, 12,678. So as with the one proportion, we showed the setup with the number substituted in, and then let the calculator do the rest. Now you can crunch this out on the calculator, on your calculator screen, and do it once with addition, once with subtraction. But it would be nice to have a shortcut, especially with this many numbers floating around. So there's a handy dandy tool that we're going to use. in our menu. So if we go to a calculator screen, go to Menu, Statistics, Confidence Intervals is number 6. Number 6 is 2 proportion Z interval. That's what we're calculating. And it's going to prompt us for everything that we need. Now, of course, it's going to use subscripts. So since I'm doing males first, number 1 is going to be males and number 2 is going to be females. Do remember that the number of successes has to be a whole number. So we're going to have to round our successes and failures to the nearest whole number. So for successes, we had 10,578.54, which rounds to 79 for the males. And the N was the sample size, so that was 12,460. We do the same for the females. I have my successes back on the last page. When I check my NPs and Qs, that's where I calculated successes. So I've already done the number crunching on those. Okay, so for women, the successes was 11,169.32, so we'll round to 69. And then the sample size was 12,678. I want a 95% confidence level, click on OK, and lower and upper bound are there. So since females were bigger than males, we're getting negatives in our confidence interval. So lower bound's negative 0.040, upper bound is negative 0.023. Now we're ready to interpret. Okay, the difference in interpreting this one and interpreting the single proportion is that we have to do comparison, which means there has to be some comparison words in there. Since these are both negative, it indicates that males have a lower graduation rate than females. So we are 95% confident that the graduation rate for males is between, okay, so I'm going to start with the big, well, let's see, yeah, 2.3% and 4.0% lower. So I'm going to kind of look at that backwards, since negatives, if you think about the number line, you kind of work backwards down the number line, is between 2.3% and 4.0% lower, there's your comparison word, than the rate for females. So you're comparing two groups, and you're making a statement about all males and all females. This is a statement about what we think the whole population looks like. To wrap that up, does this provide strong evidence that girls are more likely than boys to complete high school? Well, the entire confidence interval is negative, which implies that yes, that male rate is lower because 0's not in there. So since 0 is not in the confidence interval, and the entire interval is made of negative numbers, negative percentages, I guess, negative numbers. We have evidence that girls are more likely to get a diploma than boys. Okay, so that's it for the first round. That's everything you need to know about confidence intervals. All the structure's the same, all the checks are the same. And then next time we'll take a look at the hypothesis test for two proportions.